Hello, welcome to my presentation video on photovoltaic installations part 2. In this video, I'm going to talk about PV systems and installation rules. So, how to ensure safety during normal operation? Two particular characteristics of PV generators are their DC voltage levels and the fact they cannot be shut off as long as PV modules are exposed to the sun. The short circuit current produced by the PV module is too low to trigger the power supply's automatic disconnection. The most frequently used protective measures do not therefore apply to PV systems. However, as PV modules are installed outdoors, they are exposed to the elements. IEC 60364-7-712 stipulates that PV systems whose maximum open circuit voltage is higher than 120 VDC should use double or reinforced insulation as a protection against electric shock. And since PVs can be installed on roofs, critical attention should be paid to the risk of fire and the protection of firefighters and emergency services staff. Generally speaking, there are three situations that can lead to abnormally high temperatures and the risk of fire in a PV system: insulation fault, a reverse current in a PV module, and overloading cables or equipment. Double or reinforced insulation is a protection measure against electric shock, but it does not exclude all risk of insulation fault. DC insulation fault could be more dangerous as arc has less chance to extinguish by itself as it does in AC. The PV generator should be checked to ensure it is insulated from earth. When there is no galvanic insulation between the AC side and the DC side, it is impossible to earth one pole. AC protection can be used to detect insulation faults. When the AC side and DC side are galvanically separated, an overcurrent protective device should be used to trip the grounded conductor in the event of a fault if the PV cell technology requires one of the conductors to be directly grounded. An insulation monitoring device should be used if the PV cell technology requires one of the conductors to be resistance grounded. An insulation monitoring device should also be used when PV cell technology does not require either conductor to be earthed. Insulation monitoring device shall be selected taking into consideration both the maximum open circuit voltage and the capacitance between poles and earth causing leakage current. In addition, cables and inverter capacitance should also be considered. An insulation monitoring device able to handle capacitance up to 500 microfarad is suitable for PV systems. On this slide, you can see a table with capacitance leakage values in various PV systems provided by PV manufacturers. On this slide, you can see a table with capacitance leakage values in various PV systems measured by some European plants. A short circuit in a PV module, faulty wiring, or a related fault may cause reverse current in PV strings. This occurs if the open circuit voltage of one string is significantly different from the open voltage of parallel strings connected to the same inverter. The current flows from the healthy strings to the faulty one instead of flowing to the inverter and supplying power to the AC network. Reverse current can lead to dangerous temperature rises and fires in the PV module. String overcurrent protection is to be used if the total number of strings that could feed one faulty string is high enough to supply a dangerous reverse current. There is no risk of reverse current when there is only one string. When there are two strings with the same number of PV modules connected in parallel, the reverse current will always be lower than the maximum reverse current. So when the PV generator is made of one or two strings, only there is no need for reverse current protection. As in any installation, there should be protection against thermal effect of overcurrent causing any danger. Short circuit current depends on solar irradiance, but it may be lower than the true value of overcurrent protection. Although this is not an issue for cables as the current is within current carrying capacity, the inverter will detect a voltage drop and stop producing power. It is therefore recommended that the maximum trip current should be significantly lower than the maximum short circuit current. Where strict overcurrent protection is required, each PV string should be protected with an overcurrent protection device. The nominal overcurrent protection rating of the string overcurrent protection device should be greater than 1.5 times the string short circuit current and below 2.4 times. The nominal rated trip current of overcurrent protection devices for PV sub-arrays should be greater than 1.25 times the sub-array short circuit current and below 2.4 times. The selection of overcurrent protection rating should be done to avoid unexpected trips in normal operation taking into account temperature. A protection rating higher than 1.4 times the protected string or array short circuit current is usually recommended. Circuit breakers or fuses can be used to provide overcurrent protection. Fuses, usually on the fuse holder or directly connected to bars or cables, do not provide a load break switch function. So when fuses are used, load break switches should also be used to disconnect fuses from the inverter in order to allow cartridge replacement. So an array box with fuses on fuse holders as string protection, for example, should also incorporate a main switch. Circuit breakers offer fine-tuned adjustment and greater accuracy than fuses in order to allow the use of cables, especially for sub-array cables that are smaller than fuses. PV systems are either insulated from the earth or one pole is earthed through an overcurrent protection. In both setups, therefore, there can be a ground fault in which current leads to the ground. If this fault is not cleared, it may spread to the healthy pole and give rise to a hazardous situation where fire could break out. Even though double insulation makes such an eventuality unlikely, it deserves full attention. For the two following reasons, the double fault situation should be absolutely avoided. The fault level could be low, and below the tripping value of overcurrent protection. However, a DC arc fault does not spend itself, even when the current is low. It could be a serious hazard, particularly for PV modules on buildings. Circuit breakers and switches used in PV systems are designed to break the rated current or fault current with all poles at open circuit maximum voltage. To break the current when open circuit maximum voltage is equal to 1000 volts, for instance, 4 poles in series are required. In double ground fault situations, the circuit breaker or switches must break the current at full voltage with only 2 poles in series. Such switchgear is not designed for that purpose and could sustain irremediable damage if used to break the current in a double ground fault situation. The ideal solution is to prevent double ground faults arising. Insulation monitoring devices or overcurrent protection in grounded system detect the first fault. However, although the insulation for monitoring system usually stops the inverter, the fault is still present. Staff must locate and clear it without delay. In large generators with subarrays protected by circuit breakers, it is highly advisable to disconnect each array when the first fault has been detected but not cleared within the next few hours. Switchgears and enclosure selection. Enclosures for different PV generator boxes and switchboards on the DC side need to ensure double isolation, equipment protection against such outdoor hazards as temperatures, the rain, vandalism, and shock. Enclosure and their auxiliary equipment must ensure temperature and humidity control to allow equipment to operate smoothly. It is, however, difficult to propose a generic solution. Each installation needs to be analyzed to optimize the sizing of its enclosures and auxiliary equipment. The thermal behavior of switchgear and enclosures warrants careful monitoring. PV generator boxes and array boxes are usually installed outdoors and exposed to the elements. In the event of high ambient temperatures, high IP levels could reduce airflow and thermal power dissipation. In addition, the way switchgear devices achieve high voltage operation, for example through the use of poles in series, increases their temperature. Special attention should therefore be paid to the temperature of switchgear inside outdoor enclosures on the DC side. Cable protection should comply with requirements of IEC 60364. Part 7-712 of the standard stipulates that all enclosures on the DC side should meet the requirements of IEC 61439. This standard covers low voltage switchgear and control gear assemblies and sets out requirements that guarantee the risk of temperature rises has been factored into the safe design of DC boxes. In addition to the standard criteria for selecting enclosures in PV systems with open circuit maximum voltage of 1000 volts, some equipment may show pollution degree 2 rather than pollution degree 3. If the switchgear is pollution degree 2, the IP level of the enclosure according to IEC 60529 must be at least IP50. Overvoltage may occur in electrical installations for various reasons. It may be caused by the distribution network as a result of lighting or any work carried out, lightning strikes, or variations in the electrical field due to lighting. Like all outdoor structures, PV installations are exposed to the risk of lighting, which varies from region to region. Preventive and arrest systems and devices should be in place. The first safeguard to put in place is a medium that ensures equipotential bonding between all the conductive parts of a PV installation. The aim is to bond all grounded conductors and metal parts and so create equal potential at all points in the installed system. SPDs are particularly important to protect sensitive electrical equipment like PV inverter, monitoring devices, PV modules, and other sensitive equipment powered by the 230 VAC electrical distribution network. The following method of risk assessment is based on the evaluation of the critical length and its comparison with the cumulative length of the DC lines. SPD protection is required if the cumulative length of the DC lines equals to or is greater than critical length. Cumulative length is the sum of distances between the inverter and the junction box, taking into account that the length of cable located in the same conduit are counted only once, and distances between the junction box and the connection points of the photovoltaic modules forming the string, taking into account that the lengths of cable located in the same conduit are counted only once. On this slide, you can see a table for easy selection of SPD either for the DC or AC side of the PV system. The number and location of SPDs on the DC side depend on the length of the cables between the solar panels and inverter. The SPD should be installed in the vicinity of the inverter if the length is less than 10 meters. If it is greater than 10 meters, the second SPD is necessary and should be located in the box close to the solar panel. To be efficient, SPD connection cables to the line positive - line negative network and between the SPD's earth terminal block and ground bus bar must be as short as possible. Depending on the distance between the generator part and the conversion part, it may be necessary to install two surge arresters or more to ensure protection of each of the two parts. On this slide, you can see an example of PV system where only one SPD is installed on the DC side due to the distance between the conversion part and the generator part that is less than 10 meters. On this slide, you can see an example of the PV system where two SPDs are installed on the DC side due to the distance between the conversion part and the generator part that is greater than 10 meters. To ensure staff safety during maintenance and emergencies, disconnect devices should be appropriately located and enclosures installation should be fail-safe. The switch disconnectors on the AC side and DC side of the inverter shall be installed for inverter service and maintenance. As many switch connectors should be installed as are needed to allow operation on the PV generator, particularly to replace fuses in the string combiner boxes and generator junction boxes. For PV systems inside buildings, a remotely controlled switch disconnector should be mounted as closely as possible to the PV modules or to the point of entry of DC cables in the event of an emergency. IEC 60364-6 requires initial and periodic verifications of electrical installations. Specificities of photovoltaic installations make periodic checking very important. If usually the efficiency of all the systems is checked in order to ensure the maximum production, periodic maintenance of equipment is recommended. PV system operation conditions involve various environmental stresses like wide temperature variations, humidity, and electrical stresses. In order to ensure performances of equipment during all the life cycle of installation, particular attention must be paid to the enclosure integrity, switchgear's operating conditions, and integrity to evaluate if any overheating has or occurred to examine switchgears for the presence of dust or moisture. Visual check of electrical connections, functional test of equipment and auxiliaries, insulation monitoring device test, and insulation resistant test. We come to the end of this presentation. Thanks for watching.